And with that, I'll start off. So just real quick overview on Vitrek. You know, really industry leader, been in the test and measurement industry for over 30 years. We're headquartered in San Diego, California. We're American made, so everything's built here. Our manufacturing plant, our calibration labs, our test facilities, and all the engineering, sales, marketing is all done there. But we are an international company. We have, when we say serve over 30 countries, we have actual sales representation on the ground in over 30 countries. Yet we sell to hundreds of countries throughout the world. So we're truly an international organization, but everything is manufactured in San Diego, California. Our product lines, which we'll go through, but we kind of have a diverse group, right? Everything's in the test and measurement area. High-pot testers, which is the focus of this PowerPoint. We'll also talk about cable tests. We have a power analyzer product, which we'll talk about. High voltage meter, DC load. One of the key features is our facility is ISO 17025 accredited for calibration. So not only when the product goes out the door can we calibrate and get certified, but as you continue to use it over the years, at any time it can be sent back to our lab to do it, or obviously you can use a third-party lab. But that, you know, just another piece that we take our facility to the highest level we can in our industry. When you think about the industries we serve, it's kind of diverse, right? We're in the semiconductor manufacturers, LED lighting, aerospace, military defense is another big area, motors and drives, pretty diverse. And what really brought home during this kind of crazy time, epidemic, you know, we were getting emails and calls from our customers saying, hey, we're critical infrastructure, right? We're a defense contractor. We're making medical equipment. We're making ventilators. We're making whatever. We need you to support us. We need your test equipment. You have to be open. And I'm proud to say that our team stepped up to the plate. We figured out how to get our employees from the manufacturing into the facility, gave them proper spacing, took all definitely the hygiene that we needed to do, and sanitizing the equipment and everything else, and stayed operational and supported our customers. So it's important that we're all part of the same ecosystem to do that. What I like to do is kind of break down on the next slide the customers, right? We fall into a couple major buckets. Consumer products, whether it's Sub-Zero making refrigerators, or GE making toasters, or obviously computer manufacturers and printers is a big part of our industry, right? These consumer-oriented products. The other big category is the commercial industrials. Anybody doing any kind of big electrical infrastructure manufacturing, or anything with the medical field, like a Philips Healthcare, is another key customer. Last 5-10 years, a little longer, has really been a big push on sustainability and green market sectors, whether it's LED lighting or solar panels, electric vehicles with companies like Tesla and BMW and others. We're definitely a strong market, and that's driven by the higher usage of energy and the quality that's required there. And then I'd say the last big bucket is testing and compliance, whether it's at a lab within these companies that we just went over in the first three in their actual R&D lab, or truly third-party labs like UL, CSA, TUV. We do a lot with government labs, whether it's the military labs or Lawrence Berkeley labs. All of these areas are using our products for testing and compliance. And in a lot of cases, we have many countries using it as their standard when they test other people's products. So pretty diverse, and it's one of the good things. And we can see from the people attending this conference, you kind of fall into various buckets here. So that was also a good sign. From Vitrek's products itself, today's feature will focus on the high-pot tester, which is, really your typical electrical safety tester, making sure we're not shocking anyone, right? Pretty simple. But our market also expands beyond that. In the power analyzers, we have a full suite of power analyzers used to measure electrical power, what the efficiency is, both in the R&D lab and sometimes on the production floor. Really a high resolution, highly accurate power meter. Another area is high voltage meters. We do a lot of testing where these products go out to customers looking to test high voltage, whether it's in a lab space or from a production line standpoint or really an R&D lab. The highest level voltage, very high-end accuracy. And then our fourth more recent product is a DC load, and that is used to test products for power supplies and batteries, really looking at the full gamut: voltage, current, power, resistance, whatever else. So I wanted to show this, not to by any means be a commercial for Vitrek, but just to show you that when we talk about high pod testers, we're also able to bring in all this thought leadership we have in these other areas, and really what sets us apart as a manufacturer.
This conference will now be recorded.
More standard voltmeter, so down to a more reasonable level that there are a lot more devices capable of measuring that. And then they ratio it up mathematically based on how that transformer winds it down. Similar concept with capacitive and resistive voltage dividers. Essentially, you're going to divide the voltage down through a specific resistance and or a capacitance. Once again, to a level that can be measured with a separate, more standard voltmeter. Then you also have the technique of using a series resistance. This uses a very specialized high voltage resistor, typically multiple in series to keep the loading and the voltage per resistor down. In series to essentially convert the voltage to a very low current, which can then be measured with a precision ammeter. You also have some older style techniques, such as sphere gaps and an electrostatic measurement, which are more on the analog side. A sphere gap, you can see the picture down there at the bottom of the slide on the left. Essentially what a sphere gap would do is you have two poles, one that's energized and one that is your low return. And essentially you measure that gap between the two and you move them to a specific point in which a voltage would break down between the two poles. And based on the gap spacing when the breakdown occurs, it's in a controlled environment, you know what the voltage will be. They're not incredibly accurate, but it is a way that some people do make those measurements. You also have electrostatic measurements, which you can see in the picture down in the bottom right. Similar concept, but what it's going to be doing is the two poles will never get close enough to flash over, but instead it will use the fields generated by the high voltage side and pull a mechanical indicator, which is physically moved to indicate the level of the field that is being generated from that high voltage on the other electrode. There are pros and cons to all of the different techniques, and it really depends on what you're trying to measure, specifically what kind of frequencies and levels you're trying to measure and what kind of accuracy you're looking for. So you might ask yourself, why do I need to measure high voltage? Well, high voltage is becoming a lot more prominent in our technology and in our society all the time. Biggest reasons for this is to really increase the efficiency of all of our cabling to reduce loss in long runs. As you get higher current, lower voltage signals, you'll get a lot more loss on your long cabling. It also reduces your current carrying requirements. So with the higher voltage, you can get the same amount of power with much lower currents. So you don't need as much cable as well. So with all of these different sources being developed and introduced into our power systems in the world, there are a lot more reasons to need to measure them and validate those sources to make sure that they're applying the correct voltage. You also may need to simply monitor those high voltage sources just to make sure that there aren't any faults in the systems. They're also used in production manufacturing processes throughout various industries to either ensure that whatever high voltage systems they're using are running properly, or possibly even to dial in a specific voltage for a certain process. You may also just want to kind of validate and characterize your designs in a high voltage setting to make sure that you know what you are applying. So to go through a few real world examples, which may need to have their high voltages measured, calibrated, or monitored, you have high pot testers, something that we're very familiar with here at Vitrek, which will output a high voltage into a device in order to ensure safety of that device. With that, you have to ensure that that high voltage that you're applying into a device is very accurate so that you know that it can be safe at those levels, and you can be sure that those levels are being applied accurately. You also have things like X-ray power supplies, which require a very high voltage in order to energize the tubes which generate the X-rays, and really need to be pretty precise in order to get the proper power applied to generate those X-rays. You also have things like ion implantation, which is used in semiconductor fabrication, in which you need to regulate your electrical systems to ensure the particle acceleration that's generated through that process is functioning properly. And as I briefly discussed earlier, energy transmission is throughout the world is constantly going to higher and higher voltages to really increase the efficiency of our grids. With that come a fair amount of safety considerations as well, most of which is you have to ensure that your voltages are still being applied properly and you don't have any losses throughout. In addition, there are always new high voltage applications that are constantly being developed these days, really to get to those levels of efficiencies that are common in some other industries. For example, EV development is constantly going up in voltage from their batteries. There's a lot of development now going on that's going well past the 1 kilovolt mark that it's at about now. So talking about those safety considerations, the safety of the operator and those around them should always be your highest priority. A few things to consider when working around high voltage is that anyone working with high voltage really must maintain a really healthy respect for the risks. Only personnel who have been appropriately trained should really be directly involved with working with high voltages. You really should make sure that you establish an appropriate ground, an earth ground for all equipment involved with the high voltage process when it's required. You have to make sure that you don't introduce any ground loops into your high voltage system, as there are a lot of powers and voltages throughout the system that could cause issues with that. You always have to ensure that there is sufficient clearance around all high voltage areas to avoid any unintentional flashovers. At higher voltages in really any kind of environment condition, the voltage will flash over in a much longer space than most people realize. At specific voltages, it might jump over a foot, for example. So really having that awareness and having that space gives safety to everyone. In order to really enforce that, the use of barriers or indications of high voltage areas for any untrained individuals would be beneficial to help avoid those potential mishaps. You don't really want a untrained individual walking through a space when there's 150, 300 kV right overhead without them knowing that that's there. It's always a good point to ensure that your voltage is discharged to a safe level prior to making any physical adjustments. You don't want to just grab any wires if you don't know what potential might be on those. So it's always good to always check any of your monitoring systems to ensure that there isn't a voltage potential on that cable when you touch it. There's tools for this, such as a discharge rod that you can always use to touch to a high voltage device, as long as it's appropriately rated, to help that process along. In addition, you always want to make sure that you're following all of the manufacturer's ratings and recommendations as far as safety is concerned. Manufacturers typically, they know all of the inner workings of their sources, of their measurement devices. Always respect that their recommendations should be held to the highest standard, just to ensure safety of the technicians. In addition, Vitrek is doing another high pot safety webinar next week, which may go through some other high voltage safety techniques that may give you a little bit more insight on the safety side. So now that we've covered some of the techniques used and the safety aspects, I'd like to discuss how to properly use those techniques to make accurate and precise measurements. First, you have to identify your sources of error. There are a wide variety of sources which could influence your ability to make accurate measurements. Starting with the equipment that you're using, every single piece of equipment will likely have some sort of influence on the accuracy or the precision of your measurement. So a lot of these will be influenced by what type of signal you're measuring, whether it's AC or DC, the frequency of the signal, if it is an AC signal, as well as the calibration and the uncertainties of the calibration on that piece of equipment. This also takes into consideration if you have multiple pieces of equipment in line, you have to at least consider the error of each of those pieces of equipment as a whole. In addition, you have environmental effects on your measurements. This includes temperature and humidity. And for high voltage specifically, this also really includes altitude. With the lower air density and the higher altitudes, it really can affect how your high voltage will interact with objects around it. So it really gives a new outlook on how to control your environment at those high altitudes. In addition, you have your cabling connections. Your high voltage signals may act differently depending on how your cables are routed or what cables are being used, the quality of your terminations, for example. There's a lot of uncontrolled variables as well. You may have some invasive electrical fields that will either cause error in your sensitive measurement electronics or even on your high voltage signal. Things like EMI will come into place and also cause that kind of effect. A big one with high voltage would be corona, which would be generated from your high voltage sources. And we'll talk a lot more about corona a little later in this presentation. Really have to think about your total system uncertainty, kind of what I was talking about earlier with the equipment, taking into consideration all aspects of your system, adding up into your total system uncertainty. In addition to that, you also have to think about how your source is being loaded down by all of your measurement equipment or by whatever load you're actually connecting to it if you're doing everything in parallel. So all of that could affect how your source reacts to the load, causing an error in its output. Any questions so far?
Yeah, Brian, thank you. Just want to see on the chat line real quick, there was a question earlier, I guess related to when we discussed power analyzers and whether it measures transients, and we chatted back. Yes, our power analyzer has a built-in scope and data logger capabilities, so no problem handling all the transients from that standpoint. Anybody have any questions about what Brian has gone over so far? You can unmute if you need to. If not, we'll continue on. All right, good job, Brian. Let's keep it going.
So we do have one question from TestWave admin. So they're at 5,000 feet altitude. So at those altitude levels, so UL and ISO and IC have very specific recommendations on what kind of spacing and what kind of additional effects you may have at specific altitudes. So it might be interesting to go take a look at some of that information for your specific altitude, as they are well published.
If you have any trouble finding that information, you can feel free to send us an email, and we'll get the actual documents for you.
Certainly.
All right.
You can send them to,
yeah, because at the end of the presentation, you'll have Brian's email address will be on it. And I meant to mention this before. Everyone that's attending, you'll be getting an email with this presentation. So I meant to say that before, so you don't have to take a lot of notes, but you'll get that presentation, and on there will be our contact information. So you can send it to Brian Withers, and his email will be at the end of the beginning and end of the presentation. Thank you.
Yeah. So I think that's all the questions for now. So next, I'd like to talk about the effects of corona on your high voltage measurements. Now, I know corona has been in the news a lot lately. We are not going to be talking about that corona right now. We really want to stick with high voltage. We're also not talking about the beer. Would be nice right now, but it's not the time for it. So we're going to talk about corona and your connections with high voltages. So one of the specific sources of error when working with high voltages is really due to corona. A lot of that is due to not understanding really what corona is or how it can affect your measurements. So what is corona? Corona really is an electrical discharge into the air that generates from the electrical conductor to the surrounding substance. So typically it's to air, but it can be to other gases or liquids even. So really what happens is it will extend out and it will energize or ionize the air around your conductors or around your connections. It typically comes from sharp points, as the voltage at sharp points will have a easier path into the specific air. So one of the things to note is that corona is not prevented wholly by the insulative level of your wire. So if you have a wire with an insulation rating of 100,000 volts, for example, that doesn't mean that it will not generate any corona. It also doesn't mean that it will not be necessarily completely safe around that. So a few of the things to note on how to prevent corona is to really ensure that you don't have sharp conductive points in your cabling. So these can be really prevalent at points of connection. They can also be really prevalent if your wiring is damaged in any way. One of the goals will be to really use larger diameter wire for all of your cabling, because it's not really the rating of the insulator, it's the diameter of the cable which smooths out all of those sharp points. You know, a typical cable will be a stranded cable, which each of those strands will then be a sharp point. But if you increase the outer diameter, you have fewer sharp points to help keep that down. You can also increase the diameter by using insulative oils or a potting compound around your cabling to really give a smooth outer shell to your entire thing. Big issue with that is sometimes this introduces air pockets, so it has to be done properly, either with vacuum impregnation or just an appropriate method in order to keep those air pockets out, which then exacerbates the corona effect within the cable. Another goal will be to increase the distances, increase the gaps between surfaces. These can be conductive surfaces or even non-conductive surfaces, as voltages will be more likely to generate corona if there's a source for it to also have a potential to flash over to. One of the misconceptions is that if you cover your conductive cabling in a second layer of something like plastic tubing, then it will cut that down. What the misconception is that that will completely get rid of your corona, but really what happens is now you're just generating the corona within that tube, and it just kind of increases the air density within that space, causing more corona to generate. So if you're going to be doing tubing around all of your conductive cabling, it really should be filled with a substance that's not air. It should be filled with an inert gas or some kind of insulative oil. So moving on, with the higher voltages, larger electrical fields are generated, and typically all the equipment used is also a lot larger. So depending on your measurement technique, these can be really heavily influenced to cause error in your measurement. Many of these are predominantly AC specific, but DC measurements can still be affected in some techniques. So really any object, even your own body, can affect an electrical field if close enough in proximity to it due to a capacitive effect. So basically, if you are standing 1 foot away from your high voltage source, you're going to cause an effect to it that would be different than if you were standing 5 feet away, as your body acts as some capacitive effect to the field, and it's going to alter your measurements. So how much can it alter your measurements? Well, there are some techniques which, you know, a fist-size object within a specific space of the fields could influence your measurement up to 50%. So really there are a lot of aspects to this where you really have to be sure that you're making a proper measurement without these other effects causing that error. In addition, there are many sources of outside electrical interference that could be completely wreaking havoc on your measurements. There's things like power lines, radio stations, military installations, even poor electrical construction in your building, which could be radiating some kind of signal that could be either affecting your source or even the electronics in your digital meters, or even the measurement points in between. You know, for example, early development on electrical vehicles were not really able to implement AM radios into their vehicles because of the interference from all of the electric motors. Now, they've pretty much completely scrapped the idea of even having an AM radio in any electric vehicles because it's too difficult to keep that interference from interfering with their capabilities. So if you think about it, if you can't even have an AM radio, think about what they might be doing to your very sensitive measurements. So while minimizing the sources of error we previously discussed, there are plenty of other sources that may not be able to be minimized or may not even be considered. So one of the things you should always ask yourself when making a high voltage measurement is, are you taking into consideration all the parts of your high voltage measurement system? With the measurement device, this is the device or tool you are reading your measurement from. It's sure to have some level of error that's inherent to the product, and that should always be applied to your total system uncertainty. If you're using a divider, for example, as well, this typically also has its own level of error, which will need to additionally be considered. Most dividers also have a specific level of input impedance required of the measurement device. If your measurement device does not have the proper input impedance, this could lead to a very substantial error in your system. In addition, the input impedances of the measurement device are typically also specified with a range of values, which could even skew your measurements more. This is why it really is important to calibrate your divider and your measurement device as a system pair to ensure that everything's being taken into consideration. Things like operator bias and system location take into consideration the effects of the area and the personnel performing the measurements. It's always important to use trained personnel and appropriate equipment to minimize the operator's specific effect on your final measurement. The location of the system can also add uncertainty to your measurement, as a new location may have additional sources of error, as we discussed previously. With changes in wiring and proximity to other fields and objects changing as the system is moved. While there are other items that may also contribute to your total system uncertainty, I would like to touch on software's effect. Software should always be validated to ensure that it is not introducing additional error into your measurement. For example, if your software is not reading at appropriate times for your measurement or for your measurement device, or is performing some additional averaging, the uncertainties that may have been previously calculated based on everything else could be invalid just due to how those measurements are being performed through the software. So we'll go into another round of questions. I see TestWave admin has another question on type A or type B uncertainties. So really, type A uncertainties will typically come from things like the measurement device accuracy specifications, things like that, if you want to introduce those. For type B uncertainty, you're really going to have to do a full evaluation. A lot of those come from include some of these other uncertainties that we discussed here, as far as the operator in the system and the environment.
Also had a question before about if we supply Corona cameras, and the answer is no, we're strictly test and measure. We don't do any cameras at this time, but there's some out there. Anybody else with questions that you want to just easier to unmute your phone and ask it? We're happy to take that. All right, let's keep going.
And so now I'd kind of like to lead into the Vitrek 4700 high voltage meter. So this device is used in standards and calibration labs around the world right now. Basically, it includes measurements as AC and DC voltages simultaneously right there on the screen, along with your frequency, your peak to peak, and your crest factor, all the time right there on your digital display. So it measures up to 10 kV directly and 35, 70, 100, or 150 kV with the additional smart probes, which are developed specifically for use with this 4700. It provides laboratory standard class accuracy and reliability. They're used in labs around the world, as I said before, and listed on quite a few scopes of accreditation. It does have a chart mode, which allows you to graphically view your voltage over time. It really helps you gauge ramp times, lets you see things like overshoot, on ramp, or turn on, and sag throughout, depending on loading. It is lightweight, easy to transport. It's a little under 3U tall and a little less than half rack width. And I believe it's about 7 pounds. Does have RS-232 and Ethernet interfaces, so you can do remote communication. It's a Skippy-like ASCII-based communication system, and GPIB and battery operation are also available for increased portability if you're doing remote use. So I'd like to go through and show you how easy it is to calculate the accuracy for the 4700 using our published specifications. So our accuracies are valid for 1 year from calibration. The accuracy specifications include the measurement uncertainties in the standards and methods that we use in our labs here for every single 4700 calibration. So really the calculation is going to be a combination of the base accuracy of the product that we specify, along with the floor and the resolution. And then there's a high voltage self-heating adder as well. The direct measurement does not require any additional calculations for the accuracy at the terminal. You still need to take into consideration all of the other sources of error that might be external, but there's no additional devices that are needed when you're doing a measurement with a 4700. So there's no other devices to add to your overall uncertainty in that manner. So what's on your screen is your measured voltage, and there's a brief example down below on exactly how to perform that calculation, and you can see some of the accuracies that we can achieve there. We also have the high voltage smart probes, which are for the 4700. They plug directly into the front panel and essentially change how much voltage you're able to measure. So the smart probes really expand that capability of having that direct on-screen measurement up to that 150 kV peak level for a laboratory style probe with a base, or handheld probes up to 45 kV peak. There are also high impedance versions available for DC sources, which may have a limited power capability. These will help keep that loading down on your source. In addition, you can also make phase-to-phase measurements with 2 probes with one 4700. Simply connect your 2 probes and apply one phase to one probe and the other phase to the other probe, or differential measurements on DC as well can be made that way. So you always want to be sure to stay aware of those potential sources of error in your setup. With the larger equipment and the additional equipment, your spacing is going to be a lot more pertinent to your accuracies. So there's a nice little chart down in the bottom right there of the screen that really helps show what area has an effect around a probe, and really how you should connect it to really ensure your highest accuracy capability. If any of those are influenced within that unshaded area around the probe, you could be having very large effects to your accuracy there. So the accuracies are calculated in almost the exact same way as the direct. There's no additional adders. You don't have to take into consideration both the probe and the 4700. These are total accuracies using the probe and 4700 combined. The calibration and the identity of the probes are stored on the probe. That's what makes them smart, so they can connect into any 4700, and the 4700 will automatically know what probe it is and the calibration constants that go along with it to ensure accuracy can be used with any 4700. So our operating manual does go further into much further detail on positioning, as well as how to calculate accuracies. You can check it out on our website for more information anytime. So Vitrek is a fully accredited calibration lab. We are certified by A2LA to ISO 17025-2017 and ANSI NCSL Z540-1-1994. So it really is important to establish and maintain a documented path of traceability. It may be just as important to do so as it is to identify all of your other sources, as you may be able to state that you have a perfect calibration, but if you're not traceable back to the international system of units, then your perfect calibration could yield a very different result from another laboratory. So all standards that Vitrek uses are fully traceable back to the SI via national metrology institutes such as NIST and NRC through a documented path. So all 4700s and all the smart probes do come standard with a ISO 17025-2017 accredited CalCert, example of which is shown on the right there. Vitrek does have a variety of other test and measurement devices available, which may be able to help you expand your capabilities. I'd like to briefly talk about a couple other products which may be able to measure, help you measure or calibrate some other lower voltage devices as well, with some industry-leading accuracies. So we have the PA9XX series of power analyzers we briefly touched on earlier. These can measure up to 3.3 kV peak direct, as well as 32 amps direct. They are up to 4 channels of power analysis, so that you can achieve 3-phase measurements or efficiency measurements. Includes a wide variety of graphical functions, as well as a scope mode. Has a lot of different measurement categories that it covers, including volts, amps, watts, VA, THD, up to 500 harmonics, along with many more, rectified line, everything. We also have the Zytron by Vitrek 2000, which is a voltage, amperage, and temperature calibrator. Can measure and source DC voltage and current down to 10 nanovolt or 10 picoamp resolution. It has accuracies in the parts per million rather than the percent. It can perform temperature thermocouple simulation and measurement as an auto CJC capability, and it's lightweight, portable, and battery operated. Really lends itself to being a device that you can use anywhere in your lab or take out to field. It will help you expand your capabilities with calibrating process control devices with the 4 to 20 milliamp current loop, as it really has the perfect accuracies for those levels of measurements to really ensure that you are getting the best calibration that you can. I'll open up for a few more questions. I see quite a few have come through the chat.
Yeah, so Brian reads the chat questions. We'll repeat them for just to simplicity's sake, if anyone's got anything they'd like to ask, you can open up your microphone. Okay, Brian, you want to just, I mean, the one question was, can you use our high voltage probes with other measuring devices, not our meter?
Yeah, so the high voltage smart probes are designed specifically for use with the 4700, not for use really with any other devices.
And the other question was, do we have any videos of how to use a smart probe? What the connections look like.
We do have quite a few videos on how to set up your high voltage meters, things like that on YouTube. I'm not sure if we have one specifically for what you're looking for, but we can certainly put one up that is a great thing, a great tool to have.
Any other, I guess
yeah,
this,
we might have only had one on the direct input, so.
Any other questions? Well, if not, I mean, this is really the, I don't think there's anything else beyond this. Go to the last page, has the contact information. There is a question before about the email address. Like I said, Brian, why don't you just throw yours out right now?
So you can certainly reach me at Brian, B-R-Y-A-N, at Vitrek.com. Anytime, any technical questions you have, I can certainly take a look at you.
And that'll also be on the first page of the presentation, and you can see here, sales@vitrek.com will get you to our team, and we'll be happy to respond. All right, any other questions we have from anyone? If not, hopefully you found this informative session. Like I said, we have another one coming up on June 5th, I think. And that'll be on high pod electrical safety testing. So please go ahead. Feel free to email or ask any other questions. If not, we'll leave this open for a couple minutes as we come to an end here. And go ahead and let us know. But thank you very much for your time, and really appreciate you taking time out of your day to listen in on this presentation. Hopefully you found it effective. Brian, thank you again for your presentation.
Yep, thank you, everyone.
All right, everyone, have a good rest of your day and enjoy the weekend. Thank you very much.